Does this work? It works. Cool. So, this is my talk on optimizing WGPU with data-driven design. This is actually has some relevance to what we talked about in the last talk, and this talk will be talking a lot about barriers, how WGPU deals with them, and the challenges that come with presenting a safe and stateless API on top of a very stateful. It's not literally stateful, but things like barrier buffers have state in them, on top of a stateful API. So, who am I? I am C.W. Fitzgerald. I go by this parrot on top of my face all over the internet. I am a professional graphics and game engine developer. I'm currently the co-maintainer of WGPU and the BDFL of Ren 3, which is a WGPU 3D rendering library. Now, for those who are unfamiliar, WGPU is a safe, portable, and modern GPU API in Rust. While it is based off the WebGPU API, it runs natively on top of Vulkan, D3, 11 and 12, Metal, and OpenGL. It has become the de facto standard for GPU access in Rust. There are many both projects and libraries that are using us. Bevy, Valoran, GGEasy just moved over to WGPU. So this has become a very core library for being able to talk to the GPU and do any kind of graphics or sort of lighter compute work when you can get away with Vulkan compute as opposed to CUDA. So, if you've ever used WGPU and you've come across, you want to profile your app, you want to figure out what's taking up all the time, you'll go and profile, and there's a decent chance you'll see this one method, or in this case, this one span, taking up a good majority of your time. It's called run render pass, and we've had this mentioned in previous Rust game dev meetups, where the majority of the time is spent in run render pass. This is very consistently a fairly large bottleneck in user applications. Is us doing the work to encode the render passes that the users are writing. Excuse me. So this is a very big function, and if you actually look in the source, it's like 4,000 lines long. But we have to really understand what WGPU is doing for the user. And we present a safe API, and we're presenting a safe API on top of multiple very deeply unsafe underlying graphics APIs. Vulkan, DirectX 12, all, if you go off the rails and you disobey the spec, like, you are safely in UB land, can cause seg faults, can cause all sorts of nonsense. So we need to manage all of the problems so that when the user writes safe graphics code, it gets translated down and gets safely implemented on top of the underlying APIs. And in order to do this, there's a couple different things we have to do. We have to manage resource lifetimes. We have to generate barriers, which is something that was mentioned in the last talk. And we also have to prevent race conditions on the GPU. So resource lifetimes is fairly, it's not simple, but like it's fairly straightforward. GPUs are asynchronous. When you submit work to the GPU, it doesn't do anything immediately. It just sends it off onto this queue, and the GPU will get to it when it has some time. Which means and as part of a rule on all of the underlying APIs, you cannot clean up resources until the GPU is done with them. So if you submit and then you immediately drop all of your resources, you drop the device, you drop the buffers, the textures, everything, we can't delete them yet. That would be undefined behavior. So we must keep them alive until at least the GPU has finished accessing it and all of the references to those objects have died. There's a lot of intricate details about how to manage resource lifetimes and the countless exceptions there are, but this is sort of not is out of scope for this talk, so I'm not going to be focusing on this. But this is something to keep in mind, and something the structures that I'm talking about in this talk also deal with, and I will mention that when we get there. Second is barriers. GPUs are racy. That's just sort of an inherent property of them. A lot of GPUs are able to run do multiple things at the same time. So, for example, AMD is pretty famously known for being able to run a compute dispatches at the same time it's running render passes, even on the same queue. The issue with that is, say that you have a dispatch that writes to a buffer, and you have a render pass that reads from that buffer. There's now a dependency there. So we need to make sure that we insert barriers such that the GPU waits to start the render pass until after the compute pass has fully finished, and most importantly, all of the memory that the compute pass has written has flushed from the cache, so that when you actually start the render pass afterwards, the data will actually be buried. It won't be the previous value before the write happened. There's also some There's also some complexity with regards to textures. GPUs have very different representations of textures depending on how they're reading them. Sometimes they have, if you're rendering to them, if you're binding them as a storage texture, those all have different actual binary representations. And you need to issue barriers so that the GPU has an opportunity to rearrange the bits of the texture into whatever the next usage is going to be. In general, I'm going to refer to barriers as transitions, that is what we refer to them internally, but they're the same thing, essentially. Finally, we have to prevent race conditions. This is just one of those contracts that comes with Rust. It is racy to read something while you're writing to it. And this includes sticky situations where you have the same shader is reading the same resource as both read and write. For example, if it has it as a uniform buffer and a write storage buffer, that is an illegal condition because you can't be in both of those states at the same time. It's the same thing as with Rust. You can have a mutable access, XOR, and multiple immutable accesses. And that's the same thing with WGPU and the same thing with the underlying APIs. So that was a little bit of context about why WGPU has a bunch of stuff to do. And this is one of the ways we get these things done. These are the trackers. The trackers are responsible for keeping resources alive. All of the trackers I will show own the resources that they track to make sure they stay alive for the amount of time they should. And their other job is to keep track of what state the resource is in, so that we can insert transitions in order to make sure the resource is in the right state at the right time as the GPU is running down the code. Particularly the trackers that are in version 0.12, which is the current released version of WGPU. The details have evolved and were refined over many years, but largely structurally unchanged throughout WGPU's lifetime. The core idea worked, so we just ran with it. So the way the trackers work is essentially hash map based. All resources in WGPU have IDs, and we have a hash map from the ID to the current resource state. That's about it. For example, the buffer state is a bit flags of all the various usages you could possibly have for a buffer. Uniform storage read write, etc. And then we keep track of ref count of the object and the beginning and end state of the object. We'll get to that bit in a bit. All right, so that was a fairly abstract view. Let's walk our way through how WGPU does resource tracking, from you creating a bind group to you submitting to the you submit to the queue, but the real secret is the queue is the device in WGPU. They're the same thing. So as you submit to the device, there's a lot of points of nuance. If you really comb through this presentation, you will find things that are technically wrong that I've oversimplified. That is intentional because we would be here all day if I tried to explain everything. But this is a good overview of the flow of the data through WGPU. So you have a bunch of resources, you make a bind group because you want to bind those resources onto the want to bind the resources to a shader on the GPU. I cannot talk. So as you go through and you create this bind group, the resources are added to the bind group's tracker. The bind group's tracker owns it, so it makes sure that the resources do not die until the bind group itself dies. And then the tracker stores how the resources are used. In these diagrams, I'll be using purple to represent inclusive states. This is similar to Rust's shared references. You can have resources in multiple inclusive states at the same time. However, red represents exclusive, which is the same as a mutable reference in Rust. You can only be in one exclusive state at any one time. So in this example, we have one texture, we have two buffers and a sampler. The texture is in the storage read state. The buffer 0 is actually in two different states, in vertex and in uniform, which means that I just realized vertex buffers don't go in bind groups, but just bear with me. Pretend they do for a minute. Pretend that's another inclusive state. And then we have it in uniform state as well. Buffer 12 is in a storage read-write state, which is an exclusive state because it is writable. And samplers don't have state. They are stateless, but they are still tracked because we need to keep them alive. Nope, wrong direction. Cool. So you take this bind group and you bind it into a render pass. And render passes are special in that an entire render pass counts as one unit of synchronization. So every single resource you bind inside a render pass is treated as if you're using all of them at once. And this is so that it is actually invalid to have barriers inside of a render pass. So we cannot possibly have multiple different states that we transition between. So this whole render pass has to be basically one contiguous state. This is referred to in the code and the spec, the WebGPU spec, as a usage scope. So a render pass is one usage scope. And because of this, render passes can execute completely concurrently. Every single triangle. Well, I shouldn't say that. That's not true. But there's nothing blocking anything from being executed in any order. There's no barriers. Everything will be run contiguously. All the draws are potentially running at the same time. So when we bind this render pass, we iterate through the. Sorry, my dog is barking. Iterate through the bind group, and we add all of the resources stored in the bind group to the various trackers. So the texture, we add the texture to the texture tracker. We go through the buffers, and if you notice that buffer 0 is used in two different ways. And so we actually, because they're both inclusive, we can merge them and say this buffer will now be in both the vertex and the uniform state at the same time. This is valid because they're inclusive. And then finally, for buffer 12, we say it's in the storage read-write state. Samplers are a little more complicated, and I won't go into those. So let's say we take that buffer 12 and we turn it into a buffer 0. So we're now using this buffer 0 in 3 different ways. The problem is we can't actually do this because one of those states is exclusive. So if we were that would be a race. You would be able to write to the storage buffer and at the same time modify both the vertex and the uniform ones as you're reading them. And this is a very bad thing. There's also a lot of caches on the GPU are very non-coherent. They're not like CPU caches at all. They have to be very explicitly flushed. So you'll get a bunch of weird stale data. It will be a nightmare. So we cannot allow this. And this is another part of what the trackers do is as they're merging in these states, they need to make sure that the resulting state is valid. Vertex and uniform is a valid state, but vertex and uniform and storage read-write is not a valid state because storage read-write is exclusive. Okay, so we have successfully recorded all these commands onto the render path, and now we're in the process of finishing out the render pass and adding the render pass to the command buffer that you're encoding onto. I wrote a note that it's a smidge more complicated than this. Sort of goes without saying throughout this whole presentation. So what we do is that while I'm focusing purely on buffers here for simplicity. So this is the result of this buffer tracker here, and we're just looking at that as the result of the render pass. So we iterate through all of the buffers that are in the render pass, and then we compare them to what the command buffer currently has in its tracker. So earlier in this command buffer, apparently, it used buff 0 as a vertex and uniform. It used buff 7 as a uniform, etc. So this is stuff that has already happened on this command buffer. And remember that command buffers are sets of commands that run in, not in serial, but in order. So this is stuff that happened before. So we see that, okay, so buffer 0, it's the same state as it was before. It was in vertex as uniform before, and it's in vertex as uniform now. And so we don't actually have to do anything. However, buffer 12 was previously used as the destination for a copy. Now we need to use it as a storage read-write buffer. So we need to issue a transition. I wrote buffer 7, that's not right. A transition on buffer 12 from the destination of a copy to a storage read-write. And this happens before the render pass executes. So you have all the stuff that happened before, we issued this barrier, and then we go through and the render pass will be run once this is the transition has happened. There's a couple more rules about ordering. For example, if you have 2 storage read-writes in a row, you have to still insert a transition because you need to make sure all the writes that happened before the writes on the new render pass, but that's beyond here. So I simplified. So we've now merged the render pass into the command buffer, and now we're looking at the command buffer as a whole. So I represent the command buffer as a single tracker, but it's actually 2 trackers. So you have one at the beginning and one at the end. And if you think of a command buffer is basically a set of operations. And this, at the very beginning of the command buffer expects that resources are in a particular state because that's how they're going to be used. So, for example, in this one, at the very beginning, the 12th buffer is going to be used as the destination for a copy. So as you're going into this command buffer, the command buffer expects that the resource is in this state. So we have this beginning state and this end state. And this gives us the span, sort of the span of states, when we literally use Rust's ranges for this to represent the before state of the command buffer and the state that the command buffer leaves the resources in. if that all makes sense. If any of this doesn't make sense, please ask questions at the end. I will gladly answer them because this is a lot. I'm throwing a lot at all of you. Finally, you take this command buffer, you finalized it, and then you go to actually submit it to the device/queue. We need to do two different things. We first need to look at the state of the resources on the device. This is what the actual device, or what the actual resources the state of the resources are in after the last submission. So we've done the submission, we're now doing this new submission, and we need to look at the command buffer we're submitting and compare the trackers and say, all right, so this is what they're in before, and this command buffer expects that all of these resources are in these particular states. So we need to first insert barriers or transitions in between the last submission and this command buffer in order to transition all of the states into what the command buffer expects. Once we've issued that, we then need to update the end tracker. We need to update the device with the new state. And we've transitioned into the beginning of the command buffer, and now we assume the command buffer runs, so we need to grab the state at the end of the command buffer and update the state in the device to say, we've now executed this command buffer, all of these resources are now in this end state as opposed to the beginning state. That is why we store both states in a command buffer. Hope that all makes sense. This is crazy. All right, so I think I was a little cocky when I said it was fairly clear to understand. There's a lot going on. Again, questions at the end. This is all fine. What's the problem? It's slow. Almost all of the program time is spent inside of run render pass, basically inside of the texture tracker. And this is a report from VTune on some program. I don't remember which program I was using to benchmark. There's a couple I was using. But as you can see, it's inside the merge function of the texture tracker, or inside of run render pass, or inside of our range system, which is another thing. That's another part of the texture tracker. So basically most of these are part of the texture tracker, or this, for example, this vec call is actually part of texture impl2 merge. So this is all part of the texture tracker. So this is a problem. This needs to get faster. So I went to VTune, did a bunch of testing, and the result is we are getting absolutely destroyed by memory access. CPI is a unit of clocks per instruction. You're normally used to seeing this as instructions per clock. CPI is the inverse of this. And that means, for example, this lovely hash brown function has a CPI of 14. That means that it takes 14 clock cycles for the CPU to dispatch a single instruction. In the ideal world, CPUs can generally dispatch 2 to 3 instructions every single clock cycle. So your CPI should be about 0.3. A lot of these functions have CPIs above 1, which is not only is very bad, but in the 2, 3, 5 range, that means that we are just getting completely annihilated by our memory access. So, how do we make our memory access faster? How do we fix this? Forgot that slide was there. Here's part of the problem. Texture trackers are giant. Textures are complex. You can have a texture with multiple bitmaps, with multiple layers if you have, for example, a cube map or a 2D array texture. And we have to keep track of all of them because you can take each, what they're called sub-resources. So a mipmap and a layer, so mip1 layer 1 is a sub-resource. Mip2 layer 1 is a sub-resource, etc. So all of these things are individual sub-resources. You can use them as if they were independent resources. So we have to track all of that. Because of this, the texture tracker is giant. It's nearly half a kilobyte. And we're storing this inside of a hash map. And that means every time we look up in this hash map, it's basically a guaranteed cache miss. We're doing essentially random access into this very large data structure. We're going to be cache missing left and right. So I actually already explained most of this. Each sub-resource can be used independently. It's a very classic example to use to generate bitmaps on the GPU, where you read from one bitmap and write to the other. Then once you've written to that one, you read from it again and write to the next one down as you generate the whole MIP chain. However, if you actually look at the usages that people are doing, most resources are in a single state for the whole resource. Even, for example, if you're uploading a cube map, you have to upload each individual layer of this cube map independently. But once you're done with that, you just use it as a texture to sample from the whole time, and it's not being changed, it's not being modified. There's no real point in tracking each individual state of this cube map if it's just always going to be used as a whole resource the whole time. There's a couple use cases where you have to use every state differently, but the important part about that is that very few textures actually are in that state. They're generally shadow textures, any kind of sort of things you render to are generally in complex states. So with that in mind, we can optimize our representation of texture states. And we can split it into two parts. We can say that a texture is in a simple state or a complex state. A simple state is the whole resource is used in one way. Very common, happens all the time. And then we can have complex states, which have individual states for each sub-resource. And because of the frequency, we spend the majority of the textures we track are in the simple state, which means we only actually need 2 bytes to store every single bit of information about the state of the texture. Compare that to nearly 500. That is a very, very clear improvement. Second, the issue with hash maps. And the first instinct is, oh, it's the hash. The issue is almost never the hash, at least in our case. In our case, we use keys that are like U64s. So they're very small. Hashing them is very cheap. We use a very fast hasher because we're concerned about that. Excuse me. So the issue with hash maps is not the hashing. The issue with hash maps is the nonlinear memory access. So bringing back this example, we iterate through the right-hand side and we look up on the left-hand side. Now, depending on the particulars of the hash map and the hash algorithm, but consider that hash maps actually have randomness in them. They are they actually pull a random number when you make a hash map in order to basically randomize the hash state. And because of this, 2 hash maps with identical contents do not store the data in the same order. So as you're iterating through one of them, you're doing essentially random access into the other one. You're jumping all around this. Hash maps are stored in their underlying implementation as a vector. You're indexing into this. You're indexing into this buffer all over the place. So the CPU has no idea what you're doing. It can't predict what you're doing. It cannot. It's basically clueless every time, and as a result, will eat a lot of cache misses because it can't use something like the memory prefetcher, which will pull in memory before you need it if you're doing a simple access, like a linear scan. So, welcome to this. Well, I've been going over how the existing trackers work, and these new trackers work the same way. They do the same operations. They do the same kinds of do the same work. They are just structured differently, and they're structured by exploiting how WGPU IDs work. All of our IDs are unique. They are unique at any one time. So if you make a buffer, it gets a unique ID. If you destroy that buffer and make a new one, we reuse that ID. We have an, I don't know, is epoch, epic? I don't know. We have one of those to make sure that IDs don't get mismatched. But at any one time, there should only be one resource that has that ID at any one particular point in time. So we can use this ID as an index into a vector. And because we reuse them and we intentionally keep them as low as possible, we can make a buffer and just use that ID as an index. So this is what the new double-ended buffer tracker looks like. It is completely structure of arrays. It has multiple arrays for the beginning, the end, the ref counts, the epochs, and it has a bit vector for whether or not a resource is owned by that tracker. Because remember, before they were hash maps, so we could just not put something in the hash map if it's not owned. But now that we have a slot for potentially every single resource in WGPU that's currently active, we need to say, is this resource actually here? So merging trackers is now a linear operation, which is actually slightly worse than before. Before, trackers merging was linear on the size of the input tracker. So for example, the render pass, as we merge the render pass into the command buffer, we only have to iterate every element in that render pass. Now we have to iterate through all of them because we don't actually. It's not sparse, so it's not like we just iterate through and we get only the ones we want. We get all of them. So this sounds worse. How is it better? Running down arrays is very, very, very fast, especially if you have a small amount of data. And if you notice, every vector here is trying to be kept as small as possible, using as little data as possible, and it's stored in an SOA way so that we don't waste any bytes. So as you're iterating down these things, you use every single byte that you load from memory, and because you're iterating down arrays, the memory prefetcher knows exactly what you're doing and can start prefetching immediately. Now, the double-ended texture tracker is a little more complex, same idea, but now we have this separate sidecar data structure, which is, again, a hash map from ID to this complex texture state. When we say a resource is in a complex state, there's actually a texture use called complex, which doesn't actually get used in practice. It's not like storage or uniform, etc. But signifies, hey, this texture use is not valid. Go and look in the complex tracker to get the actual complex state. So we can store it in a nice tight U16 bit flags, and when we need all of this complexity, we can go and look it up in the hash map, find all of the various information there. So this is a hybrid sparse and dense model, and lets us get the best of both worlds. And remember, most resources will never touch the complex tracker at all. That's just there when we have to. And finally, another component of this is that we're using a bit vector for ownership. So let's say we have 50,000 total resources in the world, but we have a render pass that uses one of them. Obviously, we don't particularly want to iterate through 50,000 different states, see that they're all empty, and then skip them. So because we're using a bit vector, we can actually optimize the sparse case. And because we can load a single U size from this bit vector and say, is this 0? If it's 0, none of the resources are there. So we can skip that whole block of 64 by only reading 8 bytes, which means if you have only run one resource used in this whole thing, we only have to, despite 50,000 resources in the whole system, we only have to check about 6 kilobytes of memory. And 6 kilobytes of memory, if it's hot in cache or very well prefetched, goes very, very quickly. So this is how we get away with the dense model, despite in the logical sense, our storage is sparse, or our task is sparse. So this is where I put my money where my mouth is. These are the results. I'm testing this against Ren 3, mainly because it was the easiest one to upgrade to the Git version of WGPU, because I wrote it and I know how it works. So that wasn't very hard. This is a notoriously complex scene. It has tons of extra geometry. Every object you see has like 3 objects within it for no reason because I exported it poorly. But it's a great test scene. So, in terms of raw frame time, Ren 3 has both a GPU-powered mode and a CPU-powered mode. CPU-powered is very traditional. You bind groups for every single object. You call draw, do it again in a loop. GPU-powered is much fancier. It renders the whole scene in 3 different draw calls using bindless. But after the the new texture trackers have been implemented, we saw in terms of raw frame time a 2.5 times speed up and a 1.7 times speed up respectively because of this improvement. Now, note, this includes all other work in the program, and this program is doing a decent chunk of work outside of WGPU to prep all the state and push that all up, etc. So let's look at more submetrics. In terms of run render pass time alone, CPU powered, we're getting a 3x speed up. GPU powered, we're getting a 7x speed up. From 70 to 23 milliseconds, and from 780 microseconds to 110 microseconds. And inside of run render passes is one function called insert barriers, which is the thing that is actually doing the iteration over every single thing in the render pass and adding it to the command buffer. And this particular function sped up 14 times, and it is the same in both CPU and GPU mode. We're now down to 7 microseconds for this particular benchmark. This is incredible. It is very quick. Finally, we have some synthetic tests. This is what I was using to sort of as a unit test for these optimizations. We're looking at buffers and textures. This is a little dense. So I will explain them. So we're looking for the buffers. We have a single bind group that has 10,000 buffers in it, and 10,000 bind groups, each with 1 buffer. And as you can see, and the same for textures. And as you can see, the improvements were more for the single bind group case, but no matter what, there were improvements. The texture tracker, because of this complex to simple state change, we got tons and tons of speed up there, from 7 to 13 times speed up, whereas buffers was a little more modest, but still significant, of 1.4 to 1.7 times speed up. So this is all absolutely music to my eyes, and yeah, so now what's next? We've made a lot of progress. We've done a lot. What is next to go? profiles still show hotspots in the code. And I'm not going to get into the particulars of this because I haven't verified. Profiling loves to show red herrings, so I haven't verified any of this. But there's still many hotspots showing in the code that we need to improve on. But as we squeeze this tighter and tighter, guaranteeing improvements gets harder because you start to get to the point where sometimes the things you do to make things faster take longer to set up than actually just doing the thing. And we also have to scan over a wide variety of use cases to make sure that we aren't pessimizing some use cases, because that would be even worse. WGPU is still plagued with locking issues. We've had long-standing multi-threading problems, which are next on the docket to solve. To an extent, speed losses inside of render pass running can be helped through multi-threading, because you can in theory run multiple render passes on different threads and then submit them all at once. And finally, this sort of locking project is a follow-up to the organization with a different approach, which I'm totally not going to get into because I could also talk about this for about 30 minutes. So, why is performance important? Besides the obvious reason is going fast is good. We only actually advertise that we are portable and safe. And those are the things that we have focused on to this point. That's not to say that we haven't kept performance in the back of our mind and tried to design all of our structures in a way that is efficient and works as quickly as possible. But our promise to the world is that your code will work everywhere and you will do it in completely safe code. However, we need to be fast because we need to keep users confident in us. When people are saying that WGPU is too slow and they go and use Vulkan, they go and use DirectX 11, they go and use DirectX 12, that means we aren't doing our job correctly. People will start to look at us and be like, well, that's cute, the portability is cute, but I need the performance. And the confidence in us will slowly start to erode. And so this is, now that we've gotten to a place where we are making good on our portability and our safety guarantees. We have bugs, of course, but we're, for the most part, doing a very good job of this. We really need to focus on speed. Ultimately, WGPU wants to be the best portable graphics API out there. And ultimately, we will be. We will get there. So, yeah. If you like the work that I do, I am on GitHub sponsors. I do all this work in my free time. So no pressure at all. If you don't. Yeah. I totally got my brain. Links to things. There's this is the first time that I've actually talked about something that hasn't actually been merged in yet. The PR is still outstanding, but it will eventually go in. We've linked to WGPU and the slides, and I will also post both the slides and the diagrams I made in the meetup GitHub once we get there. And finally, thank you again to Quark for his continued support throughout everything, and thank you to the WGPU, Rust game dev, and Bevy communities for being so continuously supportive. Questions?
Great. Well, thank you so much for that. I mentioned in chat here, but it wouldn't be a CW Fitzgerald talk without a portion halfway through showing amazing numbers and speed of some benchmarks. So it's like we get all the theory and then it pays off and we see like all the improvements. Always lots of fun. A question in chat, and this might have been related to a specific part of the talk, but I'll ask it verbatim. Does the texture split state also result in memory savings here on the CPU?
It's a wash, kind of. Memory was sort of never the problem. We didn't, like, even with 50,000 textures, all in complex states, that's 25 kilobytes, which is basically negligible. Even across 100 command encoders, like that's was that 2 megabytes? Doesn't show up in comparison. So I wasn't really thinking about that. Because we now store data in a dense way, we also do waste space because we have to store these 50,000 element long vectors everywhere. But all in all, the memory used is actually not significant. The issue is mainly around cache utilization. So I actually just flat out don't have numbers on that because it was never really a problem.
All good. Another one that I was sort of wondering about myself, and it was partly answered in chat, but I'll get you to give a different answer, is when it comes to a lot of the optimizations and stuff we talked about today, how much of this type of stuff needs to be exposed to the end user as something that they need to sort of pay attention to themselves?
Absolutely zero of it. This is all completely internal APIs that we use to provide the guarantees that we do. You don't have to think about any of that.
Nice, good stuff. And let's check the game dev Discord as well, because I told people there that they could ask questions. Okay, so one question, and maybe this was like sort of answered a little bit already, but how will this impact the rest of the Rust game dev ecosystem? And I guess that's a pretty broad question.
Yeah, so your code will get fast. If you use WGPU, your code will get faster. That's basically the long and short of it. Nothing fancy beyond there. Yeah, WGPU will be faster now.
Yeah, and I think from my perspective as like a downstream user of WGPU through Valorant, where I don't actually touch any of the graphics code. Like we have very smart people that do that, but I get to play Valorant at faster FPS, and so yeah, I think that is definitely being downstream is a very nice place to be. All right. Does any of this help with mesh loading and texture loading at the Ren 3 level, slowing down the render loop?
No, that's a different problem. I'll follow up with them independently.
Sounds good. And then I guess so. Ren 3 is directly using WGPU, right?
Yes.
And so, are you able to use like Ren 3? Like, do you use it as like an example of what could be improved in certain ways, or like you having done Ren 3 gives you ideas on WGPU, or what's how is like the symbiotic relationship work there?
Yeah, very very much that way. This is actually driven by performance reports that I get in Ren 3 saying, "Hey, I like upgraded the version of Ren 3 and performance got worse." And so we started investigating that, and one thing led to another, and I ended up at this this is the bottleneck that needs to be eliminated first. Is this run everything inside run render pass, and to an extent, it's still the bottleneck. It's just faster now. So there's still more to go. As I said, there's still hotspots to squeeze down. We are continuously improving. But yes, Ren 3 has driven a lot of the improvements that I make to WGPU because it makes things. People use it, and when people use it, they spot issues, and I bring those issues down to WGPU to make everyone's life better.
Nice. Another question: couldn't the state changes, or at least some of them, be tracked directly when recording the render pass instead of doing it at queue time?
That is a very good question, and the answer is no. The thing is, if you're recording a render pass, you're recording a render pass onto the command buffer, and excuse me. You could, for example, run a render pass on command buffer 1, run a render pass on command buffer 2, and then submit them in the other order. You can submit the second one first, and then the first one second. And because of that, we don't actually know the full chain of states on the device until you submit. We do know it in the command buffer because the command buffer is a linear set of commands, but we don't know how those command buffers actually merge together onto the device until you submit. So we can't do that immediately, even though we would love to. In an API like GL, you could, because there is a single global state, but we know that that is horrible for many reasons. And this also lets you do things like parallel command recording, where each command buffer runs separately. There's an interesting point to be made. Things like APIs like Dawn. Dawn is Chrome's implementation of WebGPU. And Dawn actually defers all of this until submit time. They don't actually record their command buffers until you submit the WebGPU command buffers. And this allows them to have a much more global view and have a single, like, I can see all the states at once, which is useful to an extent, but it also means that you don't get the benefit of the user's able to multi-thread. The user can now like take a command buffer, record it over there, record this over there, all on their own, and then submission is a fairly lean process for us. Whereas with them, they have to go and actually record all the command buffers for all the work that they did. There are pros and cons to both of these, but for us, being able to give the users as much control as possible to make us as much like the native APIs is very important to us. So to an extent, we inherit more complexity in order to give the users that guarantee.
Great. And so I think that's it for questions. And so we will end off the meetup here for today. But Connor, thank you so much for the talk. It's always great having like these longer form ones, and I definitely want to see more of them in the future.